This episode of SpaceTime is brought to you by Audible.com. Over 180,000 titles to choose from for your iPhone, Android, Kindle or MP3 player. Get a free audiobook download and 30-day free trial at www.audibletrial.com/spacetime. That's www.audibletrial.com/spacetime for your free audiobook. This is SpaceTime, Series 20, Episode 92. Coming up on SpaceTime, new questions about dark matter and dark energy. Is antimatter the hidden face of lightning? And Trojan Martian asteroids created by sunlight. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study is raising fresh questions about dark matter and dark energy, two of the most mysterious and least understood features in the universe. Professor Andre Mader from the University of Geneva has developed a new hypothesis which attempts to explain both the accelerating expansion of the universe and the movement of stars and galaxies without needing to draw on the concepts of dark energy or dark matter, which he says may not actually exist. For close to a century now, scientists have hypothesized that the universe contains far more matter than what can be directly observed. They call this mysterious invisible stuff dark matter. They've also postulated on the existence of dark energy, a force more powerful than gravitational attraction. In both cases, dark matter and dark energy, the dark refers to science's lack of knowledge and understanding. These two hypotheses, it's been argued, account for the movement of stars and galaxies and for the accelerated expansion of the universe. But Mader argues that these concepts may no longer be valid because he believes the phenomena they describe can be demonstrated without them. His research, reported in the Astrophysical Journal, exploits a new theoretical model based on the scale invariance of empty space. Back in 1933, astronomer Fritz Zwicky made a discovery which left the world speechless. There was, he claimed, substantially more matter in the universe than what can actually be seen. Astronomers called this invisible substance dark matter, a concept that was to take on even more importance in the 1970s when astronomer Vera Rubin called on this enigmatic matter to explain the movements and speed of stars and galaxies. Stars seem to be rotating faster than what they should based on the amount of mass those galaxies appear to have. But so far, all attempts to identify a dark matter particle have been without success. Meanwhile, in 1998, astrophysicists studying thermonuclear or Type 1a supernovae discovered that the universe's rate of expansion out from the Big Bang 13.8 billion years ago appeared to be accelerating beyond gravity's ability to retard that expansion. And despite enormous resources that have been invested to try and explain the observations, scientists are yet to reach agreement over its likely cause. Worse still, neither dark matter nor dark energy fit into the standard model of particle physics, science's key foundation stone for explaining the universe at its most basic level. Mader's new model, based on the scale invariance of empty space, is designed to do away with both problems. The way we represent the universe and its history are described by Albert Einstein's equations of general relativity, Sir Isaac Newton's universal gravitation, and quantum mechanics. Mader says the model consensus of a Big Bang followed by an expansion doesn't take into account the scale invariance of empty space. In other words, the empty space and its properties do not change following dilation or contraction. Of course, empty space plays a primordial role in some of Einstein's equations because it operates in a quantity Einstein referred to as the cosmological constant. Of course, for Einstein, that turned out to just be a fudge factor. However, the resulting universal model we now have today still depends on it. Based on this hypothesis, Mader is now re-examining the model of the universe, pointing out that the scale invariance of empty space is also present in the fundamental theory of electromagnetism. When Mader tested his new model, he found that it matched the observations. He also discovered that the model predicts the accelerated expansion of the universe without having to factor in any particle or dark energy. Mader then focused on Newton's law, a specific instance of the equations of general relativity. The law is also modified when the model incorporates Mader's hypothesis by incorporating a small outwards acceleration term which is especially significant at low densities. When applied to clusters of galaxies, this matter-amended law leads to the masses of clusters falling in line with that of the visible matter, and so no longer needs the additional missing mass to explain the high speeds of galaxies and clusters. Mater says the amended law also predicts the high speeds reached by stars in the outer regions of galaxies without having to turn to dark matter in order to describe them. This is SpaceTime. I'm Stuart Gary. The Murchison Widefield Array Observatory has reached a key milestone in its ongoing development with the completion of its Phase 2 expansion. The work, which has taken nearly 16 months, includes 128 new antenna stations at the observatory site in outback Western Australia. The latest additions bring the total number of antenna stations on site to 256. The Murchison Widefield Array is one of 4 precursor facilities for the multi-billion-dollar square kilometre array project, which is building the world's largest radio telescope spread across 2 continents. Murchison's also the only one of those facilities that's already fully operational. The observatory is a low-frequency radio telescope operating between 70 and 300 MHz. It's pursuing a diverse range of scientific programs, including performing a survey of the entire southern hemisphere sky and acquiring deep observations of targeted regions. The radio telescope spans a 6-kilometre diameter area. It uses 4,096 dual polarization dipole antennas arranged as 256 phased array antenna tiles. Each tile consists of a 4x4 array of 16 dual polarization dipoles, measuring 5 metres by 5 metres in size. Project Director Associate Professor Randall Waith from Curtin University says the new antennas has significantly increased the research capabilities of the $50 million observatory. By doubling the number of antennas and quadrupling the size of the area they're distributed across, the telescope's now 10 times more powerful in its exploration of the evolution of the universe, with an ability to discern details twice as fine as previously. What all that means is that astronomers can now not only explore more of the universe, but the sensitivity and quality of the data they receive is also vastly improved. The Phase 2 rollout began in mid-2016 with the deployment of 72 tiles arranged in a regular hexagonal configuration that became operational in October last year. The remainder of that rollout, 56 additional long baseline tiles, began at the start of 2017 with the antennas positioned between July and October. This upgrade not only increases the capacity of the Murchison Widefield Array, but also greatly adds to the team's understanding of what's to come on an even grander scale with the rollout of the square kilometre array across Australia and South Africa. Waith says the observatory will improve science's understanding of an era in the universe's early history when the very first stars and galaxies were turning on, in the process ending the cosmic dark ages and beginning the epoch of reionization. It's a period of the universe science knows very little about, so having the increased capacity of 128 new antennas to build on the work already being done is crucial to the research.
The upgrade consists of deploying 128 new antenna tiles. So we call our antennas tiles because they're kind of a little grid of antennas that all work as one single unit. And the deployment is for a few reasons. It improves the sensitivity and the resolution of the array by a factor of 2 just for sort of normal imaging modes that we use. And 72 of the new tiles that we deployed are really specifically for one of our key science cases, which is the epoch of reionization science case. And that deployment of antennas is really optimized for that science case and improves the sensitivity by almost a factor of 10. So it's a real improvement, and it's a really nice milestone for us to have met when we only commenced operations in mid-2013.
The epoch of reionization that you've just mentioned, this is an important milestone in the history of the cosmos. It's really when the first stars and galaxies began to shine.
Exactly.
It's an incredibly important time.
About 13 billion years ago, when the first stars and galaxies were forming, the universe was really just a fog of hydrogen gas that was just beginning to collapse into the first galaxies. And this is a period of the universe that we currently know almost nothing about. And the reason for this is, one, it's a long time ago and far away, so it's really difficult to see, but also also, because there were very few stars and galaxies at this time, it's quite difficult to access with conventional telescopes, like an optical telescope, because there just weren't many stars, so there's not much light. So this is really exciting and important for us to sort of fill in the missing pieces of sort of like the family photo album of the universe, where we really don't know much about this time. And what happened during this time in the universe has really sets the picture. It sets the sort of the initial conditions for everything that happened afterwards. And so what happened then ultimately has determined what the universe looks like today. So we really are quite excited about this because we don't know anything about it, and it fills in the last piece or the missing pieces of the jigsaw puzzle of our model of the universe.
This is when population 3 stars dominated the universe. These were very different from any stars we see around us today, and they're very important because they were made out of virtually pure hydrogen and helium, maybe a little bit of lithium, the pure elements of the Big Bang. And it was from these population 3 stars that, well, all the other elements on the periodic table, including the iron in your blood and the oxygen you're breathing, the calcium in your bones, the carbon which we're based on, that all came as a result of those first stars.
Yeah, that's right. So this is one of the reasons also why we're so interested in studying this early period of the universe, because as you say, that these first stars, these so-called population 3 stars, none of them exist anymore today. And so we have to sort of infer their properties and what happened to them, how many there were, how big they were, from their effect on the universe at that time. And so by studying this epoch of reionization, what actually happened during this time, that is a way for us to sort of indirectly infer the properties of these first stars. And it's also worth mentioning, of course, that these first stars were also, they're thought to be the progenitors of the first black holes in the universe. And it's still not clear. It's still an area of active research to figure out how it is that we get supermassive black holes, like really, really big ones, billion times a solar mass in today's universe and even in the universe many years ago, because it's not really clear how you can grow such massive black holes in relatively short periods of time. So, yeah, understanding these population 3 stars, how they seeded the heavier elements in the universe and whether they were the source of these progenitor supermassive black holes is really, really important questions.
The new James Webb Space Telescope, which will be launched either next year or the year after, it depends which press release you read, that hopefully will allow us to see this period visually. What does Murchison do? How does Murchison view this time in the universe's evolution?
Yeah, that's a really good point. So the James Webb Space Telescope and the MWA and the other radio telescopes that are trying to access this period, they're really quite complementary, right? So James Webb Space Telescope is an infrared telescope, but like conventional telescopes, it will target relatively small patches of the sky and study in detail specific objects, relatively small number of objects. So this is actually looking at the light from these first stars and galaxies. The way the radio telescopes like the MWA work, they are looking at the faint radio signals from the hydrogen gas in the early universe. And this is telling us what's happening on a much larger scale. So we're not really studying individual objects. What we're studying are the sort of statistical properties and the large scale properties of what's happening with galaxies, the first galaxies on a galactic scale and larger.
This is the big picture you're looking at.
Yeah, exactly. So the two telescopes are really quite complementary on what they're trying to do to study that period of the universe.
And these large survey telescopes, this is what the Australian section of the SKA is really going to be focusing on, isn't it?
The future radio telescopes, in particular the low frequency telescopes, just by their very nature, they have a very large field of view compared to normal optical and even other radio telescopes. And that naturally lends them to doing surveys. So observing very large fractions of the sky or even the entire sky and being able to extract that information out on sources that really cover the whole sky. So MWA is a really good example of that. You know, we have already surveyed the entire sky visible to us at the radio frequencies that we work and published a catalogue of all of the objects that we found. And these survey data products are really, really valuable. They get used by thousands of scientists in ways that we wouldn't have originally dreamed of as the people who thought of doing the survey in the first place. So yes, really, really important products, survey work.
I understand that the new tiles that have been added to the MWA have already provided some great new images, radio images of Fornax A.
Yes, that's right. So So the new tiles, we've just reconfigured the array into what we're calling the extended configuration. So this doubles the resolution and the sensitivity compared to the original deployment. And yeah, we've made some really nice images of Fornax A. So far, everything's looking really good. And we're looking forward to doing another sort of upgraded survey of the sky, plus all of the other targeted observations that we do. And in the future, we will be looking forward to what the next upgrade path for the MWA is. There are a number of options that we're considering at the moment, but maybe on a 2-year timescale or something like that, we'll be looking at making that next leap of improvement.
The other big angle of this, of course, is the huge amounts of data that will be coming back from the antenna.
Yep.
New ways of processing have to be developed in order to go through all that data. This is a big challenge for the SKA project as well.
It's a big problem. Problem's not the right word. It's a big challenge. That's absolutely true. So the MWA, at the moment, since operations commenced, we've collected, I think, about 17 petabytes of data. So that's a lot of data. And it's not the kind of volume of data that you can process on your workstation sitting on your desk anymore. This is the kind of stuff that needs to be processed by supercomputers, and we make heavy use of the Pawsey Supercomputing Centre in Perth. And you're right. So it's the kind of volumes that require really new ways of processing it. And so the data-intensive astronomy and the big data aspects of this are extremely relevant. And MWA, in many respects, is kind of showing the way for future SKA. So SKA will be even bigger again compared to MWA, probably by a factor of 10 in terms of their data rates and data volumes and things. But having MWA between now and SKA is actually probably a really good way for everyone to come up to speed. And one of the things that we're really proud of with MWA is that we're really training the next generation of radio astronomers and data scientists how to handle the massive volumes of data that we get from these new radio telescopes.
That's got to be a bit of a concern. You don't want to wind up throwing out the baby with the bathwater, so to speak. But when you have all that much information, you're going to have to look at ways of culling that down to what you really need. And there's always the fear that something really significant is going to be missed. How concerned are you about that?
Oh, that's absolutely true. But I mean, that's true really for any modern observatory, not just radio telescopes. The volumes of data that we get are huge. I mean, the way that these things are typically handled is that unusual events are detected because they have some property that makes them stand out from the rest of the sources and things like that we observe. And it's that unusual property that makes people have a second look and look in a bit closer, and that's when the interesting discoveries are made. So the fact that it is not a perfectly blindly automated data processing pipeline, there are still people involved. There are humans who need to look at the quality of the output and double check and sanity check and all that kind of thing. And that's when the interesting discoveries are made. And the other side of this, of course, is that once you have huge data sets and you have extracted millions of interesting radio sources and things out of these sets, then looking at the statistical properties of those and the outliers of the properties of those sources, that's also where you discover the interesting things. So I share, I mean, we all share your concern with this, but the fact that people are still involved, people still look closely at the data, and it's not a fully automated, non-interactive pipeline means that the interesting things do get caught. Is
there a further upgrade coming of what we're seeing now, pretty well what the MWA will be?
No, we have plans for further upgrades. It's going to, it's dependent, of course, on some successful grant applications and things like that. But, one of the great things about MWA is that we, as a precursor for the future SKA, where we have many of the similar science goals in mind. And so we're learning through processing our data what needs to be improved, what sort of unexpected things have popped up. So we already know that we need to make some improvements to some of the signal processing and things like that. And so that will probably be the focus of a next upgrade. So definitely that's not the last of it.
That's Associate Professor Randall Waith from Curtin University. And this is SpaceTime. I'm Stuart Gary. It's been discovered that terrestrial gamma ray flashes, produced in lightning from thunderstorms, can also generate antimatter. A report in the journal Nature claims terrestrial gamma ray flashes react with the air to produce radioisotopes and positrons, the antimatter counterpart to electrons. The study's lead author, Teruaki Enoto from Kyoto University, says scientists already knew that thunderclouds and lightning emit gamma rays and hypothesized that they would also react in some way with the nuclei of environmental elements in the atmosphere. In 2015, Enoto and colleagues started building a series of small gamma ray detectors, which they positioned along Japan's western coastal area, a region ideal for observing powerful winter lightning and thunderstorms. 4 of those detectors, installed at Niigata, recorded a large gamma ray spike immediately after a lightning strike a few hundred meters away. When the authors analysed the data, they found 3 distinct gamma ray bursts. The first was less than a millisecond in duration. The second was a gamma ray afterglow which decayed over several dozens of milliseconds. And finally, there was a prolonged emission lasting about a minute. The first burst was from the lightning strike itself. The second, the afterglow, was caused by lightning reacting with nitrogen in the atmosphere. You see, the gamma rays emitted in lightning have enough energy to knock a neutron out of atmospheric nitrogen. And it was the reabsorption of this neutron by particles in the atmosphere that produced the gamma ray afterglow. Enoto and colleagues determined that the third and final prolonged emission was from the breakdown of the now neutron-poor and unstable nitrogen atoms. These released positrons, which subsequently collided with electrons, and when matter and antimatter meet, they annihilate each other, in the process generating gamma rays. I'm Stuart Gary. You're listening to SpaceTime. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. A new study claims some of the Trojan asteroids orbiting with Mars could have been created by sunlight. The red planet Mars shares its orbit with a handful of small asteroids known as Trojans. Trojans are asteroids trapped in gravitational dead zones in a planet's orbit around the Sun. These gravitational dead zones, or Lagrangian points, are locations where competing gravitational perturbations from two bodies balance each other out. Any object at that location will equally feel the gravitational tug of both bodies and will therefore be able to remain there in a stable orbit. There are 5 Lagrangian points. Using Mars and Sun as the example, the first 3 are all on the line connecting the two and close to Mars's orbital track. The first of these, the L1 position, is between Mars and the Sun. The L2 position being around the opposite side of Mars from the Sun, and the L3 position being on the opposite side of the Sun from Mars, in other words, on the other side of Mars's orbit. The remaining 2 Lagrangian positions each form an equilateral triangle with Mars and the Sun. The L4 position being 60 degrees ahead of Mars on its orbital track around the Sun, and the L5 position being 60 degrees behind Mars on its orbital track around the Sun. While many of the Sun's family of planets have Trojans, Mars is the only terrestrial planet known to have Trojans in stable orbits. Among them is a unique group all moving in very similar orbits, suggesting they all originated from the same object. However, the mechanism that produced this group is a mystery. Now, astronomers using computer simulations think they've identified plain old sunlight as the culprit. If correct, their findings highlight how small asteroids near the Sun may evolve. The first Mars Trojan, discovered over 25 years ago at the L5 position, is named Eureka in reference to the famous cry yelled out by ancient Greek mathematician Archimedes. The present tally of Martian Trojans is 10, but they seem to show some orbital structure not found in Trojans elsewhere. For starters, all but one of the Trojans are trailing Mars at its L5 Lagrangian point, and all but one of the L5 Trojans form a tight compact group, with 2-kilometre-wide Eureka its largest member, and including objects as small as just a few hundred metres across. Scientists have been working to try and determine how this family of Trojans came to be. It's known that collisions, which occurred hundreds of millions to billions of years ago, formed similar families in the main asteroid belt between Mars and Jupiter. But the problem is an impact origin doesn't work for these Trojans because the group is so incredibly tightly compacted, only the very gentlest of impacts, with the fragments barely able to escape Eureka's gravity, would result in the formation that astronomers are seeing. The models show that even impacts with just enough energy to break up Eureka are so rare that they wouldn't happen over the age of the solar system. Also, we know that the Joukowsky effect would cause family members of this group to slowly drift away over billion-year timescales. The Joukowsky effect is a tiny acceleration caused by sunlight that's absorbed on one part of the asteroid. As the asteroid rotates, the stored heat is re-emitted as infrared radiation, acting as a kind of tiny amount of thrust on the asteroid. Okay, so none of that works. Taking a step back, the team adopted a different approach, looking at the Martian Trojans as a whole group instead of just focusing on this one family. From this perspective, the lack of a family around the two remaining Martian Trojans, 10, 14, 29, 1998 VF31 at the L5 position, and 12, 15, 14, 1999 UJ7 at the L4 position, becomes an important clue to the puzzle. Both these asteroids are at the same distance from the Sun and of similar size to Eureka, yet we don't see other asteroids grouping up near them. So that's got to be telling the scientists something about how these families can or can't form at Mars's distance from the Sun. That something is very likely rotational fission, driven by what's known as the Joukowsky-O'Keefe-Raszewski-Paddock effect, or YORP effect for short. It's a similar effect to Joukowsky and also driven by sunlight, but changes the asteroid's rotation rather than its orbit. The scientists think this is causing Eureka to spin up. In other words, its rotational speed is increasing. Eventually, it's rotating fast enough to fling off bits of the asteroid. These then escape to become independent asteroids orbiting the Sun. Importantly, Eureka rotates every 2.5 hours, and that's just about as fast as an asteroid can spin without flinging apart. And recently, the team observed the L4 asteroid, 1999 UJ7, finding that it's spinning about 20 times slower than Eureka, in other words, only once every 2 Earth days. Other slow-spinning asteroids of this size are found to be in a tumbling state, where, at least in theory, YORP may switch off. UJ7, therefore, may simply be incapable of producing new asteroids by flinging bits off. This explanation, however, doesn't work for 1998 VF31, the remaining Trojan at L5. It's rotating about once every 8 hours, and that's not slow enough to prevent the YORP effect from spinning it up to the point where it's flinging bits off. But since we don't see any new asteroids, something must be happening to them after they leave VF31. To find out what, the team ran a computer simulation, following the orbits of virtual asteroids produced by both VF31 and Eureka under the Joukowsky effect. They found that whereas Eureka offspring can survive at L5 for more than 1 billion years, VF31 is sitting close to what I guess you'd call a dynamical escape hatch, allowing any bits breaking off the asteroid to escape from its Trojan prison within 200 to 300 million years. And the result of that would mean no family for VF31. To test their theory, the team are now planning to look for fainter Trojans under 100 metres across that may be orbiting Mars. Finding lots of these small Trojans near Eureka, and perhaps a few near VF31, but none near UJ7, would indicate their hypothesis is likely to be correct. Of course, if they are right, it means that once you're close to the Sun, the YORP effect-induced fission, essentially the action of sunlight, may be just as important for driving asteroid evolution as collisions. And that's important, because if there are any stable Trojans orbiting with Earth around the Sun, then the YORP effect could be turning them into sources for new near-Earth objects. This is SpaceTime. I'm Stuart Gary. Okay, let's take a quick break from the program so I can tell you about our new deal. We have a great offer for listeners of SpaceTime. Audible's offering a free audiobook download and a free 30-day trial. How about Earth Shadows by Daniel Aronson, or Not Alone by Craig A. Faulkner? So many great books, no matter what your taste. Over 180,000 titles to choose from. And no need to rush. Not only do we give you a free book, but you'll have a 30-day free trial to browse to your heart's content. To download your free audiobook today, go to audibletrial.com/spacetime. Again, that's audibletrial.com/spacetime for your free audiobook. Or you can click on the link at spacetimewithstuartgary.com or in the show notes. And now, back to the show. China's busy rocket program remains in top gear with its 14th launch for 2017 blasting into orbit. The latest mission, the third this month, involved a Long March 2C rocket flying from the Xichang Satellite Launch Center in southwestern China's Sichuan province. The 42-metre-tall two-stage Long March 2C carried 3 satellites described by Beijing state-run media as remote sensing probes for scientific experiments. In reality, the payload comprises 3 top-secret Yogang 3002 military surveillance satellites designed to eavesdrop and gather signals intelligence data from other nations from a 600-kilometre-high low-Earth polar orbit inclined at 35 degrees to the equator. The latest flight follows the launch of 2 of Beijing's new Bidao 3 navigation system satellites aboard a Long March 3 rocket earlier this month from the same launch facility. The new navigation satellites will provide users with global position accuracy down to 2.5 metres. That was followed a week later by the launch of a Long March 4C rocket carrying the new Fengyun 3D weather satellite from the Taiyuan Satellite Launch Center in Jiangxi Province in northern China. The 2,200-kilogram second-generation meteorological satellite was placed into a polar orbit. The spacecraft carries 12 scientific instruments, including a multispectral imager. As well as atmospheric observations, including microwave and infrared emissions, the new probe will also monitor space weather events and atmospheric ozone concentrations. Only one of China's 14 space launches held so far this year has failed. That was in July when Beijing's new 57-metre-tall heavy-lift Long March 5 rocket failed, following its launch from the Wengchang Satellite Launch Center on the southern Chinese island of Hainan. The mission failed to reach orbit while carrying the Shijiang 18 telecommunications satellite. The Long March 5 can carry up to 25 tons into low Earth orbit. It's designed to help China achieve its ambitious manned spaceflight program. Beijing's plans include a permanent Earth-orbiting space station and a base on the Moon as part of helium-3 mining operations on the lunar surface. China still has 2 more launches slated for this year. A Long March 3B rocket carrying Algeria's first telecommunications satellite is slated to fly on December 11th from the Xichang Satellite Launch Center. And a Long March 2D rocket will launch in late December carrying 2 Super V1 Earth observation satellites from the Taiyuan Satellite Launch Center. I'm Stuart Gary. You're listening to SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. All the signs indicate planet Earth is about to enter a mild La Nina weather pattern, either late in December or in early 2018. The Bureau of Meteorology reports the tropical Pacific is approaching La Nina thresholds. If the current progression continues and thresholds are exceeded for a sustained period, 2017-18 will be considered a La Nina event. As a result, the Bureau's El Niño Southern Oscillation outlook has been raised to La Nina alert status, meaning there's approximately a 70% chance, or triple the normal likelihood, of La Nina occurring. Mind you, climate models suggest that any La Nina event is likely to be weak and short-lived. This means it's expected to be very different from the strong 2010-2012 La Nina. Oceanic indicators of the El Niño Southern Oscillation show a very clear progression towards La Nina. Tropical Pacific sea surface temperatures have cooled since late winter, and waters beneath the surface remain cooler than average in the eastern Pacific. However, they're currently just shy of La Nina thresholds. Still, atmospheric indicators such as the Southern Oscillation Index and trade winds have shown signs of shifting into a La Nina-like state. In order for La Nina to become established, both atmospheric and ocean indicators need to be coupled. In other words, they need to reinforce each other. Such actions would strengthen and sustain these changes, providing a positive feedback. The bottom line is that all international climate models are suggesting further cooling of the tropical Pacific is likely. All the current models are forecasting La Nina thresholds in December, and most maintain these values until at least February next year. La Nina typically brings above average rainfall to Western Australia during late spring and summer. Problem is, sea surface temperature patterns in the Indian Ocean and closer to Australia aren't yet typical for La Nina. That reduces the likelihood of widespread summer rainfall. Meanwhile, a new study has confirmed that hot El Niño weather patterns dry out tropical forests, causing predictable patterns of wildfires. A report in the journal Nature Climate claims that lower rainfall in northern Australia reduces the amount of fuel on the ground, thereby making fires less common in the year after an El Niño event. However, in wetter tropical forests throughout Asia and the Americas, fires increase, releasing more carbon into the atmosphere. To reach their conclusions, scientists used satellite data from 1997 through to 2016, encompassing some 6 El Niño and 6 La Niña events. They found that fires follow a predictable seasonal progression across tropical continents, which may help forecasters in future predict fire risk. A new study by researchers from the Murdoch Children's Research Institute has shown that an alarming 40% of Australian adolescents with food allergies are experiencing frequent allergic reactions, including anaphylaxis. The new findings are based on a study of 10,000 children aged 10 to 14. A report in the Journal of Allergy and Clinical Immunology found that among the 547 kids with food allergies, 50% had experienced an allergic reaction in the past year. Almost 10% reported potentially life-threatening anaphylactic reactions, and adolescents reported that reactions occur most commonly in the home. And while we're speaking of Australian adolescents, it seems energy drinks are now the most popular sugary beverage among Australian kids. Now, a new study reported in the Australian and New Zealand Journal of Public Health warns that a new generation of energy drinks are more strongly linked to dental problems than traditional soda pop soft drinks. Researchers found that frequent toothache was more common among the 50% of teens who regularly drink at least 1 cup of sugary drinks per day, and the link was strongest for flavoured water, energy and sports drinks. The study also found that energy drinks were more consistently linked to being overweight or obese. A new study warns that increased levels of air pollution have been linked to poorer quality sperm. The findings are reported in the Journal of Occupational and Environmental Medicine. Researchers looked at the semen of 6,500 men over an average of 2 years. They then compared the results to estimated levels of fine particulate air pollution around each of the subjects' homes. Scientists found that increased levels of air pollution was linked to having a lower proportion of sperm of normal shape and size. The authors say that although the study cannot show cause and effect, and that the effect they found was small, it's still an important public health challenge because air pollution is so widespread. Air pollution has already been associated with a huge variety of adverse effects on humans. Particulate air pollution, especially very fine particles of 2.5 microns or less in diameter, can reach deep into the lungs, delivering potentially toxic complex combustion products and heavy metals into the body. And finally for now, a new study says drinking coffee is more likely to be beneficial to health rather than harm it. The findings, reported in the British Medical Journal, claims that drinking 3 to 4 cups of coffee a day was associated with a lower risk of death and getting heart disease compared with drinking no coffee at all. Coffee is one of the most commonly consumed beverages worldwide. The research, based on over 200 studies, also found that drinking coffee was associated with a lower risk of some cancers, a lower risk of diabetes, a lower risk of liver disease, and even a lower risk of dementia. However, they found drinking coffee in pregnancy may be associated with some harms, and it may also be linked to a very small increased risk of fracture in women. Researchers found the best health benefits from drinking coffee came from those who had 3 cups of coffee a day, compared to non-coffee drinkers. Increased consumption above 3 cups a day wasn't associated with any harm, but the beneficial effect was less pronounced. Coffee was also associated with a lower risk of several types of cancers, including prostate cancer, endometrial skin and liver cancers, as well as type 2 diabetes, gallstones and gout. The greatest benefit was seen for liver conditions such as cirrhosis of the liver. Finally, there also seemed to be beneficial associations between coffee consumption and Parkinson's disease, depression and Alzheimer's disease. There was less evidence for the effects of drinking decaffeinated coffee, but it still had similar benefits for a number of outcomes. The authors conclude that drinking coffee seems to be safe within usual patterns of consumption, except during pregnancy and in women at increased risk of fracture. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, @SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Today's episode of SpaceTime was brought to you by Audible.com. Help support the show and get your first book for free plus a 30-day free trial. Use the link www.audibletrial.com/spacetime for your free audiobook.